Okay, so last time we were talking about this business here about how to use double integrals to solve problems, right? And it's a tricky bit because on the one hand we can connect applications directly to double integrals. That's really nice. That's why we need double integrals. You can't just take an application and start writing down iterated integrals. It doesn't make any sense. On the other hand, we know how to compute iterated integrals. Right? So we were thrilled to note that you can always turn a double integral into an iterated integral, and that gives us our three-step process for being able to solve problems right here like so. And last time we went through an example showing those three steps. You can see right here, 1, 2, and 3. And I want to pick up from this discussion last time. We were talking about phase 1. Here, taking the application and producing a double integral. Okay, so keeping in mind what a double integral is, it's a Riemann sum. Right, that's really important. Right? So we produce the Riemann sum, and then we say, hey, by the way, don't forget we have this handy double integral notation. And after all, that's all this is just a notation to represent a Riemann sum. That's what's really happening. Right? Okay, so the observation can be made that, look, if I'm going to eventually rewrite a limit of a sum with integral notation as, a little double integral symbol there, and if I am eventually going to rewrite delta x, delta y as dA, why don't I just go ahead and use that handy, convenient notation throughout the process? And so, for example, instead of writing, when I claim the whole is the sum of the parts right here, and chopping up the whole mass into a bunch of little pieces of mass, right? Okay, well, I can say the exact same thing, just using kind of integral shorthand, if you will, right? And write it like this. And this kind of thing is just very convenient. So it's very common. That's the main motivation, by the way, for this next example, is that this notation is a convenient shorthand while you're developing your Riemann sum in the first place. Okay, so let's look at this example. We have a wall. The idea is that this is maybe the facade of your house or something like that. And these days they have these really pretty stone kind of facades on houses. Well, if the wall in question is 10 feet wide and 6 feet tall, as indicated by that rectangle right there, right? Here's the thing. I mean, the stones that are eventually going to make up this stone facade, they're on the ground. That's where the truck dropped them off. They're at ground altitude, and yet they're going to have to be picked up a significant amount of altitude, and that's going to take work, right? So how much work is it going to take to do that? Various complications to this question because, this stone here has to be lifted that amount, but the stone that's going to be over there is lifted a smaller amount. Yes, but this stone here has one value of density, the the weight per unit area at that point on the wall is one thing, but at this point on the wall, the weight per unit area is different. Right? So there's lots of factors that are going to play into this. How are we going to sort of put it all together and compute the total amount of work? And it turns out a double integral is the exact tool that we need for this, and furthermore, that this integral shorthand's convenient for this purpose. So here we go. My first observation, and I very often will just write this down, just even if I personally don't need to write that down for my, I've been doing this for a while, right? But still, I like to doff the cap to the fact that work is an accumulating quantity. The whole is, in fact, the sum of the parts. Right? The grand total amount of work for the whole wall is the sum of how much work it's going to take for each little piece in the wall. Okay. Now, for a given little piece, right? Given let's talk about that little piece of the wall right there. How am I going to compute that amount of work? Well, it's force times distance. And you can see the force and the distance right here in the story. So this little piece has a certain amount of weight to it, right? That little piece of the wall. I've got a formula for density, right? We'll get to the actual how to compute the weight, but that piece of wall has a weight. Keep in mind, weight is a force, right? It's not the same as a mass, right? And conveniently, we're interested in force, not mass. And so having been given force per unit area, everything's exactly what we need, and that's nice. So there's the force, and you can also see that that piece is going to have to be lifted this far, whatever the y-coordinate of that point in the wall is. That's how far I'm going to have to lift the stone that starts off on the ground, and I'm going to have to lift it that amount to get up to where it's going to be placed in the wall. Okay, so this first move here, in other words, writing down the amount of work that it takes for that one piece, work is equal to force times distance. And you'll notice I'm using this integral shorthand. Keeps everything kind of compact and neat and clean and convenient. Okay. All right, now, question. Yeah, how much does that little piece of wall weigh? What is that little differential force? Well, weight is weight per unit area times area. And luckily, we are given weight per unit area right there. Right? So that tells me, pounds, for example, per square inch or per square foot or whatever the units are. It doesn't matter. Okay. All right. So again, notice I'm using the differential shorthand. It's very convenient, and it allows me to develop the integral. So now, look at what we have all together. We have that work is this expression right here, which is a double integral. Now, I could have, I suppose, written all this out with limit and summation, and I could be, put in all the little nitty-gritty little details. But why would I bother? It's just going to turn into a double integral anyway. It's just easier just to start writing it with that same notation. Okay. At this point, it's kind of all over but the shouting. We have an entire wall that gives these bounds for x and y. We have an iterated integral that we can plug and chug, and the answer ends up being this value right here. So that's just details. Y'all have seen that kind of thing several times before, so I'm not going to spend class time on that part. But do make sure to go through and check and make sure that you're comfortable with all that stuff. Okay. All right. Now, new topic. What do you do if your domain is not a rectangle? That's a problem. If you think about it, it's a problem because all these examples that we've seen previously, here we have a rectangular wall. Here we have a rectangular sheet. Here we have a rectangle over which we're computing volume. Everything that we've done, the only Riemann sum for double integrals that we've written down is specifically for rectangles. Not everything in life is a rectangle, right? So how are we going to deal with the non-rectangular case? And here's the good news. Ultimately, almost exactly the same thing. Practically every aspect of dealing with non-rectangular domains is just exactly like with rectangles. So, for example, and I'm going to go with the loaf of bread metaphor because it's easy to visualize. Okay, so here's our loaf of bread. How are we going to compute that volume? Well, the whole is the sum of the parts. The whole volume of the loaf is the sum of the volumes of the slices of bread. Okay. The volume within one of these slices is cross-sectional area times thickness, just like before. That cross-sectional area, if I want to compute this cross-sectional area, is still an integral because it's still the area under a curve that curve still being the graph of a given function. This is all exactly the same as before, right? So that means that the function whose graph I'm looking at is my integrand, and I am still, of course, going to be integrating from some starting point to some ending point. And now here's where the one difference kicks in, getting rid of the mess here. When I look at this area, hang on, highlighter. When I look at this area as this integral, let me zoom so I can see better. We are going to have x kind of going across these values like that. There's going to be a starting value of x and an ending value of x that will be our x bounds. And the only difference is that now those are functions of y instead of constants. That's it. Everything else is exactly the same. Now, let me elaborate on how they are functions of y, I claim that these bounds depend on y. So, for example, suppose you have a given value of y. For that given value of y, we're sort of going across this y slice, like so. Well, for that value of y, this point determines our starting value of x. And this point determines our ending value of x. But if I went to a different value of y, let's take a value of y, let's say right here. What about that value of y? Well, for that value of y, the little slice of bread is much thinner, you'll notice. It's a tall, skinny little slice of bread. And so in computing that integral, I will be going across this domain where the starting value will be this different value of x. Right? And then likewise, this ending value will be, again, a different value of x. So you can just see right here in the picture, as these y's move, because these edges over here are curves, as you change the y, you're going to change the corresponding x's representing your starting value, likewise representing your ending value. Said differently, these bounds depend on y. Said differently, these bounds are functions of y. All right, how are we doing? Does everybody see that? Pretty believable? Yeah. Okay. All right, cool. Now, here's the thing. How are we going to find those functions? And are we really going to have to draw this three-dimensional picture every single time? And good news, no, we don't. I tell you what I am going to do, though. I'm going to clean this up just a little bit. You know what? Let me just start all over. Real quick, our process for a given value of y, we're looking at a y slice, and then we start at that point, which you're going to notice is on that curve right there, and that determines for us our starting value. We end, again, same thing, we talked about this before, that point, which is on this curve, which gives us this ending value. Notice that everything we need here to determine these bounds is entirely inside the xy plane. The vertical stuff, the height, doesn't have anything to do with these bounds. Right? All the vertical tells us is, the vertical, how far you have to go up to get to the surface, that's what tells you your integrand. Yeah, sure, but we already know the integrand. We already know that our integrand for our iterated integral is exactly the same as our integrand for our double integral. That part's easy. Right? So we don't really need the three-dimensional version of this diagram. So let me redraw now this diagram. Same diagram, but now just looking at the two-dimensional version of it, because that's all we need. Here it is. And for a given value of y, There's our y slice. Okay, now pause. What do you mean y slice? What does this have to do with anything? Don't forget, we're actually computing a cross-sectional area, right? The reason we're going across this y slice is so that I can, for this inside integral, I can compute that cross-sectional area of our actual three-dimensional thing. Yeah, sure, fine, right, cool. But as far as the bounds are concerned, all I need to notice is that this is what that shadow looks like in the xy plane. I don't need the height. I again can argue that x is going to start at that point, which determines that bound by way of whatever equation I have for that curve. And likewise, x is going to end when I get to that point on this curve, which again gives me my upper bound. So, same picture. Here, in our original picture that we felt comfortable with because it shows the entire volume and you can feel like you see what you're actually computing. Arguably more satisfying in a way, but harder to draw and completely unnecessary. This is much easier to draw, much more practical to work with. So this is what I encourage when you're trying to answer one of these questions, when you're trying to turn a non-rectangular domain into iterated integral bounds. Just draw the two-dimensional version, right? And just this is all you have to think through right here. Okay, we got a bunch of examples to talk about. Okay, here's the first one. Our domain is a triangle. Certain vertices given. There it is. We're going to ask how to compute this double integral right here. Now, real quick pause. Why? Where did this double integral come from? I made it up. It doesn't matter. What is the relevant application? I don't know. Doesn't matter. Maybe I'm computing mass, and x plus y gives me my mass per unit area. Maybe I'm computing the population on this, and this gives me people per unit, people per square mile, whatever. Maybe there's mass. Did I say that one already? I think I did. And anyway, bunches of different examples that you could possibly choose from that will give rise to a double integral. We're just going to entertain, given the double integral, how do I turn the double integral into an iterated integral? That's what we're going to focus on. So don't worry about the application. Don't worry about what the x plus y means. It doesn't matter. Okay, so following the pattern from our picture, seems I'm doing my x slicing on the outside. So I claim x goes from 0 to 1. And here are those x slices. Something like that. You can see it starts over there at 0. It ends at 1. Why did I get the 0, by the way, as the start? Well, because that starting point is that point, and I can see the x-coordinate right there is 0. Likewise for the ending point. Okay. All right, so my outside bounds 0 to 1. Now, I'm going to fix a value of x. I'm going to follow the pattern in this diagram here. For a given value of my outside variable, starting with the starting point, I'm going to identify the relevant point. That point is on a certain curve. That curve will have some equation. And then I will solve for x in this case, whatever the inside variable is I'm trying to find the bound of, I will solve to then get the lower bound as a function of the outside variable. Okay, so same thing here. Variables reversed. Again, doesn't matter which way you slice. For this value of x, looking at that x slice, now I'm interested in how y varies along that slice. And we start at this point right there, which is on this curve, which has that equation. By the way, let me pause real quick. I really need the picture. I'm relying heavily on the picture. It's the picture that tells me, oh, okay, well, if I do a slide, okay, well, apparently this is the curve. Right? Don't try to rely on the algebra. Don't look at the givens of the statement of the question for the intuition for which curve. There's three curves in this picture. Which one tells me my lower bound? The picture is what will tell. Right? So that point on this curve is what's going to determine my starting value for y. Okay, so keeping in mind that I am trying to solve for y here, looking for a y bound, within this equation here, I need to solve for y as a function of at most x. And you can see y right there starts at 0. Okay, now looking at the upper bound. The upper bound, how do I know when I'm done on this x slice? Well, I'm done as I go up this x slice, right, when I get to that point. That point is on this curve. So that point, whoops. What's going on? Oh, my stylus ran out of power again? Come on. Okay, I'm sorry. Pause, I gotta plug in my silly little stylus. Last check. Yeah, no, it's out. Okay. Just a quick second. Okay. Right. Okay, so so yeah, this point is on that curve. Again, thank you, picture. Got to use the picture here. The picture is what tells me as I go up my outside x slice, when I get done, right? Where does that x slice end? It ends at that point on this curve. Thank you, picture. Don't try to figure it out from the algebra. It's a big mistake. It's really inconvenient at best, if not impossible. Okay, so this point, this equation. Now, quick reminder, what are we doing here? We've already got our x bounds. We're trying to find our y bounds. This point, then, on this equation, I need to solve for y. So I'm looking for a y bound. So I need to figure out how this equation, y equals x, will allow me to view y as a function of x. And that y is a function of x. Very easily, it's just x. Everybody okay? Everybody see the process? All right. Okay. Cleaning up the mess here. Okay, now I'm going to do the same example again. I'm going to do the same example, but this time I'm going to slice it the other way, just to show that you can, and that depending on the specifics, it doesn't really matter much, as long as there's no reason that it might. But we'll talk about how to decide between the options in a couple of minutes. But same story, this time with y on the outside. There's my range of values for y. Here's my y slices. Again, looking at the picture, you can see where my first y is, where my last y is. Y is going to range from 0 to 1. Those points are, in fact, given. So y goes from 0 to 1. Okay, now we focus on a particular y slice. So setting y, let's say at that value. Looking then at this y slice, x is going to start at that point, which is on that curve, which has this equation. Remember now, what we're doing here, and especially given that we just switched the differentials, it's easy to lose track of, wait a minute, which variable am I trying to find the bounds for here? I don't know. I find that confusing. Maybe you find it confusing too. I like to pause and remind myself I need to solve for x. So I'm looking for an x bound. So I need to find a way to view x as being a function of y, and x viewed as a function of y is computed with that formula. X is just y. Everybody good there? Very importantly that it's y. It's not x. It's y. Everybody happy? Okay. Yes?
And so this is just proof that you can reverse it and get the same.
Yeah, well, proof's a strong word. It's just an example. I'm just showing off that you can do it either way. Totally. Yeah. Okay, upper bound real quick. That point, which is on this curve, which has that equation, x equals 1. Again, now I need, keep in mind, I'm looking for a value of x. And so in this equation, I need to solve for x as a function of y. And that's an easy formula. X as a function of y is just, 1. Constant function. Super good. Very convenient. Everybody good? And again, details, plug and chug. Y'all know how to do those. Okay, so that's our process. Now, there's many examples to be discussed between the examples I'm going to need to show you for other purposes that are about to come up and the examples that we're going to see when we get to triple integrals. Let's see, when's that going to be? I guess Wednesday. We're going to see so many examples of this slicing process. I'm going to start moving a little bit more quickly. But this is the strategy, this is the process, and please do make sure to adhere to this process. I want to address one fact. There are a lot of high school multivariable calculus courses out there, or, I don't know, other places you might have taken multivariable calculus courses. I've seen students come with lots of, oh yeah, a little algorithm. This is what you do is you take from the statement of the question, you take this part and you just put it here, and that's the formula for your inner bound and stuff like that. You cannot trust these methods. They rely on an assumption that the example you've been asked fits into a very narrow category, and they will work only for examples that fit in that narrow category. They won't work for other examples. So you really do have to think it through and very slowly and carefully. So make sure that you adhere to this thought process and don't rely on little symbolic manipulation techniques or whatever they would call them from previous classes. They're not to be trusted. Okay. So, next example. Again, I'm going to do this two different ways. Same example, two different ways. We're going to first slice dy dx. We are then going to slice dx dy. Then we're going to look at the results. We're going to ask which one of these results do we like better. And then we're going to ask the very natural question, how can I avoid having to write them both down in order to decide which one I like better? How can I just always go right to the good one, right? And cut my workload in half. Several things to be said here. So again, we're going to move quickly through this. There is a comment-worthy thing at the beginning. If I look in the x direction, there's my range of values for x. Here's my x slices. You can see covering the entire region there. And the starting and ending, you will notice, starting and ending are at these 2 points. And how do I find those 2 points? Well, those 2 points are on curves. They're on that curve and this curve. I'm looking for points that are on both of those curves because I'm looking for where they intersect. Again, thank you, picture. The picture is what tells me that. Okay? Right, so I need to solve, keeping in mind that I am looking for values of x. Here, I shouldn't have used blue. That's right, I meant dark blue. I'm looking for values of x, and so within this pair of equations here, I need to solve for x. The thing I want to point out here, of course, y'all can do the little algebra. It's not hard algebra. But there is a tricky little bit. A lot of people would solve for x and get 2, and that's a mistake. Just try to remember the squaring function is not invertible. You can't just take the square root to solve an equation that has a square in it. Right? There's always that whole business about plus or minus. Very common mistake for students to make. Secondly, I will point out that when you do solve and get 2 and minus 2, how do you know which one goes where, aside from a reasonable guess? The negative one should probably be less, and therefore the lower bound. Right? That's a reasonable guess. But really much better is to let the picture be your guide. I'll point out, for example, that to find this upper bound, this algebra tells me 2 or negative 2, but I can look at this point. I can see where that upper bound is, and I can see that in the picture it's unambiguously positive. So I'm going to pick the positive of my 2 options because the picture demonstrates that it should be. Excuse me. Likewise, for the lower bound, the picture clearly shows that the lower bound has to be negative, and that's why I'm going to pick the negative of those 2 square roots. Okay, so there's that. Let me also point out, y'all can think through the rest of the details of this one. Let me point out again that when you're trying to find the inner bounds, let's see here, let me go back to green, looking at y is going from there to there. There's my y slice. Fixing a value of y, fixing a value of y, let's say here, there's that y slice, looking for our inner bounds coming from these 2 points, giving these 2 bounds. Notice again, those points are on that curve, and on that curve, need to solve for x. And again, I have a square root situation. So again, don't forget about the whole plus minus, and also don't forget that the picture will show you by virtue of, well, which one's positive, which one's negative, or which one does the picture show must be the greater versus the lesser. Let the picture be your guide, and that will make your choices for you, and thus these 2 bounds. Okay. The rest of the details I'm going to let y'all read through. I think this should be straightforward read at this point. Make sure you're good with it. What I want to get on to now is which one of these integrals do we like better? I mean, I think it's pretty clear that we should like this one here, right? And I don't like this one. Now, let me be explicit about why I don't like this one down here at the bottom. I'm going to have this x integral to do, no problem. These square roots don't really come up in finding the antiderivative of f with respect to x. That's fine. And then when they do come up, it's after I've done the antiderivative, and yeah, square roots are weird and all, but you just plug them in to whatever the antiderivative is. No problem, it would seem. Here's the problem. The problem is not the x integral. The problem is that this whole x integral, including what I get when I plug in these square roots that I don't like, that's the integrand for my outer integral. So the dx integral here would be no problem. Well, it depends on f, I suppose, but presumably no problem. Certainly no problem coming from the square root of y and the minus square root of y. Where these square roots are going to start to stink is when you get into doing the dy integral. They will be part of the integrand for that dy integral. And as y'all remember from single variable integrals that have square roots in the integrand tend to be a lot harder. So, so that's why I have these preferences. Now, natural next question, how do I avoid having to write both of these down? How can I see this coming? And here's my little trick. I think this is very convenient. Starting with the integral on the top, I had dy on the inside. That means that in order to find these bounds, I needed to solve for y in that equation, and solving for y in that equation is cool. No problem. A, it's already been done. More to the point, I like the result of solving for y in that equation. It's just a polynomial, nothing ugly. And that's why I get what I'm going to call good bounds here. Right? Now, by contrast, what happened to these inside bounds? Well, I had x on the inside, which means I needed to solve for x in that equation. And solving for x in this equation is what makes square roots show up. Right? And I had to solve for x because of the fact that I put the dx on the inside. Right? And that's why you get these bad bounds. So my rule of thumb when such a circumstance arises is if I look at an equation and if I see pretty clearly a preference, like I would much rather solve for y than for x, not because it's been done, that's not the point, because I like squares much better than square roots. Right? When you find yourself in that situation, identify which variable you'd rather solve for and put that differential on the inside. That'll avoid this as best as possible. Does that make sense? All right. Okay. Another example. We're going to do two different ways. How are we doing on time? Yeah. Okay. So we've got a triangle, corners given, picture you can see. Again, double integral that we want to compute. Don't worry about where the double integral came from. Doesn't matter. We're just looking at phase 2. We're looking at how to turn double integral into iterated integrals. Again, we're going to consider two different orders for the differentials. Dx on the inside, dx on the outside. Try it both ways, see what happens. Starting with y on the outside. Y goes from 0 to 1. Here's my y slices. Right, looking at one in particular. Looking at that y slice for this value of y. The lower bound for x is going to come from that curve. Right, and then the upper bound for x is going to come from that curve. Particulars and details, not the point here. You can see the range of values for y, and you can see which curves the x bounds are going to come from. Okay, now let's look analogously down here. And let's see here. I will use, how about I use, okay, that's good. Let's put dx on the outside. X would appear to go from 0 to 2. Our y bounds then are going to start on that curve and are going to end on this curve. And here's where the problem starts to show up. I know I'm going to need to write down the equation of that curve and that curve. And wait a minute. I don't have an equation for this. There's two equations. There's the equation for this part over here, and then there's the equation for that part over there. They're different equations. Okay, so I can't really do it that way. What I have to do is change my strategy to looking only at the 0 to 1 values for x, where the lower bound is going to come from that curve, and the upper bound is going to come from that curve. And then I have to consider a whole new separate integral as x goes from 1 to 2, where my lower bound is going to come from, well, in fact, the same curve as it turns out, but then my upper bound comes from the different curve. Right? So looking at, looking at these two, looking at that and this, those upper bounds being different is because we have these two different curves that those upper bounds came from. So this is a bummer. This is significantly inconvenient and bad because, well, I'm going to have two separate intervals to be computed. And by the way, the dx integrals, the outside integrals for each of these are going to be different because you're plugging in different values into y on the inside integrals. So we will have literally different integrands for our dx integrals in this example. So this is a lot more effort. Roughly double, not quite, but ballpark of double the effort. Now, why did this come up? And again, how can I avoid this problem? The way I like to think about it is that the problem was that the thing that gave rise to this bad news here is this corner. And it's not so much that it's a corner, it's that this is where one equation jumped over to a different equation. It's because I have really two curves here, and this is where those curves intersect. And when curves intersect, that's typically where you're going to see a corner. Right? Yeah. Mm-hmm.
Is there a way that you could write it so that it is one equation, like negative absolute value of x or something?
Yeah. I mean, you could get real clever with it, but then the problem is that that's something that you're going to have to plug in when you do the inside antiderivative, and then that's wacky formula involving absolute values. Now that's part of your integrand for your dx integral.
Gotcha.
And I don't know we don't have formulas for that. So really that's a temporary workaround at best. And so punchline, you are going to have to compute two separate intervals. Yeah. I mean, good thought, but it doesn't work. Yeah. Okay, so the problem was that corner. And the way I like to think about this, and this is just a point of view, but this is how I like to think about it. As I go through and slice, try not to slice through a corner. Anytime you slice through a corner, you're going to have to stop the integral you're developing and start a whole new integral. And you can see that happening right here, right? We had to stop as we were doing our x slices. When I sliced through that corner, I had to stop that integral and then start a whole new integral for x for the remainder because I sliced through a corner. Now, you could point out, and you'd be right, that technically I kind of sliced through corners in this example too, but the thing is, when I sliced through those corners, I was starting a new integral there anyway. It's not really a problem, right? And then throughout the interior, no problem, no corners, everything's smooth. Now I sliced through a corner at the end, but I was done anyway. So again, no problem, right? So try not to slice through corners in the middle of your slicing process. That's the big takeaway. Okay. We good? Here's a piece of good news. We have two different kind of examples here that we've seen. You can do it both ways, and which one's better, and little strategies for how to do the best possible job. I can't say that this is always the case, but the good news is it is usually, at least in my experience, the case that when this point of view about input and output variables gives a suggestion for which way to slice, and when this corner business gives a suggestion for which way to slice, in most cases, they suggest the same order of slicing. So you don't need to worry about so much, anyway, about these conflicting with each other. If they both come up, then they tend to both agree. What I will point out, though, is that sometimes, in fact, in these two examples that we're looking at here, only one might show up. Like with this, the first example up here, there's no corners in either direction. So this business about corners is irrelevant to guiding you on this first example. And then if you look at this example down here, do I really need to worry about y being a function of x or x being a function of y? No, they're all straight lines. Who cares? It's just as easy to solve for one in terms of the other or vice versa. So this business about input and output variables is irrelevant to this example. So you need to understand both of these strategies to be able to advise you on different kinds of examples. And the good news is they won't conflict. Okay. One more example before we finish this section. Let's see how we're doing on time. Okay, this will be all right. Okay, sometimes the domain is not explicitly given. Easy example here. In fact, let me see if I can just switch to this. Are we back in business? Yeah, we're back in business. Okay. Fine. So, let's see here. We have a paraboloid. We have a plane. We're interested in this region that's kind of between them. We want to find the volume there, right? The double integral portion of this is a pretty straightforward discussion. You look at this business right here, you can see that the volume of any individual French fry, as I like to think of them, right? That volume is actually pretty easy to compute because it's just going to be height times area of the base. There's going to be a little tiny little area of the base, which is part of our little domain down here. That's going to be area. And so this volume is just that times that, and voila, double integral. Nothing to it. The question, though, how do I understand the domain? And this is something a lot of students get wrong. A lot of students don't necessarily know quite how to proceed, and they kind of make something up that doesn't work. So I want to first show you the wrong method so that you can know what not to do, right? And then I'll show you the right method. So here's the wrong method. It's going to start off right. We understand that domain by trying to understand that perimeter curve. That perimeter curve is the shadow of this intersection. That intersection is where both of these equations hold. After all, it's where this paraboloid intersects with this kind of plane. Right? So the students correctly reason that I need to find values of x and y that make both of these work at the same time. And here's where the students go wrong. The students then figure, okay, I have two equations. I'll set the equations equal to each other. And students will write down that equals this. And I say that's a bunch of nonsense. It doesn't make any sense at all. I mean, why do we set the right side of one equal to the left side of the other? Why not set the left side of one to the right side of the other? Right? Notice, furthermore, you can manipulate these equations around. I could rewrite this one on the right as 4x plus 8y plus 2z minus 7 equals 0. Should I set this equal to that up there or this down here? Right? Endless examples of why this is meaningless nonsense. Right? So don't set equations equal to each other. That's not a thing. It's just not. Okay. So that's the wrong method. Now let me show you the right method. The right method is to realize that what we're looking for here are values of x and y, points like this, that are on this curve. And in particular, I want to know values of x and y where if I ask what's the z value that gets me up to the paraboloid and what's the z value that gets me up to the plane, I want those two z values to be the same. That actually makes sense, and let me be consistent with my coloring. I want these two things to be equal. Because for the x's and y's I'm looking for, the plane and the paraboloid intersect, which means the height up to the plane and the paraboloid are the same height. In other words, that these two z's are equal. So this is conspicuously different, of course, from the nonsensical setting the equations equal to each other. You have to do a little bit of work to figure out what this z is right here, for example, and that turns out to be this. And of course, solving for this other z is easy. That's just that. So this is the equation that describes our perimeter right here. Okay, now just a real quick reference. Notice that completing the square is necessary to sort of, simplify this equation so you can see what you actually have. So just a quick reminder, please do make sure that you're good. Oh, wow. With completing the square. And then notice the final punchline is we have a circle. Okay, see y'all later. Have a good one. Picking up here on Friday.
And the end would be the equation of the domain.
Hang on just 1 second here.